understand that whenever we have a motion, and if we try to restrict the motion, we are putting some constraint to it. The problem becomes simpler if you can actually consider the generalized coordinate. So as a result of which, like if you consider just one coordinate instead of two, and those two coordinate is dependent on that one coordinate, the number of equations that we have will become lesser in number. So less number of equation, less trouble, right? Mathematically less trouble. So we are trying to do that in classical mechanics, and that is what we are going to trying to do it here. Okay? We are going to realize this fact. Today we are also going to look into something additional, that's how exactly do we get acceleration due to gravity g as nothing but acceleration. Okay, that is if you consider rate of change of velocity, or d2x dt square, that give you acceleration. Okay, how does it related with acceleration due to gravity? That idea can also be seen here using classical mechanics. So last class we did see about virtual work, and we did say that if we have a system where we have an applied force and we have got an force due to the constraint, and then if we consider the idea or the concept of then the force due to the constraint vanishes. Okay. So applied force, what exactly do I mean by applied force? So I said the other class that if we have a system, let's say a balloon, and you are applying some kind of force from the outside, this will be basically your applied force. And the force that is being applied by, let's say, the walls of the balloon, which is actually a constraint, or the individual collision that happens because of the gas molecule, are nothing but the constraint forces. Okay, so you can actually modify or manipulate these forces. Suppose I am not applying any pressure, I am applying some heat, then the gas molecule will try to vibrate, move at a very fast pace. So these kind of modifications can also be done. So whenever you are doing any kind of research, okay, I think you have basic idea, not very advanced idea. You will have that idea later in your semester. But if you have a very basic idea, people do consider experimental physics as something which you can explore more. But that's not the case. When we talk about theoretical physics, even classical mechanics also has a lot of experiment left. Okay, a lot of things which can be done. So these are not more theoretical rather than experimental work. There, what happens is people simulate a system. They apply some let's say I have some, with advancement of technology we have those softwares, okay, where you can simulate a system. You can simulate an electronic circuit, you can simulate a gas system, you can simulate a closed enclosure. Okay, everything can be simulated. And when we basically simulate a system and we apply some kind of heat, let's say, and we see how the system changes, we can actually relate it with the real life experience, and we see that this more or less tallies with whatever you see in real life. So these things are not something which we can ignore. Okay, we need to study these things. So based on this, we said that of course the applied force dot product of the position vector will basically give you 0, also, which is basically delta Ri. So that is the displacement. So what I mean to say here is that individually we cannot say that applied force is 0. Of course not. There has to be some kind of force so that actually I can study the system. So individually it's not 0. When we are considering force multiplied with the displacement, this is basically 0, right? So this is the work done. Okay, so we have got force into displacement, which is nothing but the work done. So the case is something similar, because I think you already have this idea that if we have the angle between force and displacement to be 90 degree, okay, you basically have the work done to be 0. Now then, this is a case which we have studied before, and here we are looking into more of a classical picture where we are not considering the angle directly, we are saying there is a virtual displacement. One more example I'd like to tell you, which we are going to come across today. What do you mean by exactly a virtual displacement? So imagine any object is falling from the sky, and it is falling under the effect of gravity. Okay, and then because of this gravity and of course the viscous drag of the air, we can say that the object has got slight displacement upward also while it's falling. Okay, so it might be at any particular moment. Okay, So these are all like ideas or concepts. Okay, you cannot really visualize it that easily. It takes some time. We're going to look into those things maybe later, okay, if time permits. So the virtual work of the applied forces must also vanish. So this is what we have seen, and this is called the principle of virtual work. But then the question is, does this force that we are talking about, does this force that we have, is it a function of just force, or we can actually write it down in some other coordinates also? Okay, so we're going to see that these coordinates will be important, but not now. So for this, we are going to look into something which we call as the D'Alemberts principle. So it's nothing but an addition to this virtual work problem. Okay, we're going to add more to this virtual work problem. So what is D'Alemberts principle? So let's just read this sentence. Consider a more general case where the system is not necessarily in equilibrium, so that the net force on the particle is not zero. So what does it say? It says that this is more of a practical system. If we say that there is virtual displacement, and we say that the forces which are acting on it, or the system is in equilibrium, okay, this is more or less ideal case. It's an ideal case. It's not a sometimes may not be a practical case. So if you want to actually have a practical case, we say that the system is not in equilibrium. Okay, so whenever we say that a system which is classical in nature is not in equilibrium, that means it has got some velocity associated with it. Okay, and of course there is some mass. So that means there is some momentum which is there in play. Okay, so we are going to include momentum in the equation now for the virtual displacement. Okay, so we have this. Then but the case here is we still don't know the constraint. Okay, the constraints are still unknown. So what we are going to do is we are going to use this equation to find out the constraint. Okay, so the idea is simple. Try to think about it. Okay, we are not considering an equilibrium system. We are considering a system which is not in equilibrium. So if a system is not in equilibrium, that means the particles, the force that is acting on the particle is not zero. Okay, so if you consider, let's say, a gas molecule, and a molecule somehow breaks the balloon, okay, it basically is not an equilibrium system anymore. Okay, so if we consider the principle of virtual work, we said that the system was in equilibrium. And if we include the dynamics here, so you know there are dynamics, right? You kinematics usually we say, and something in motion will be dealt under this particular topic, which is called the dynamics, okay, or kinematics, and we will include the Newton's second law, right here. So what we do is here that if we have motion, we are including Newton's second law. So the rate of change of momentum is directly proportional to the impressed force and takes place in a direction in which the force acts. Okay, so you have to remember your Newton's three laws, and you will see that more or less these are applicable here. Classical mechanics very well relies on Newton's laws. Okay, so we are going to use Newton's second law, and then if you look into the Newton's second law, the rate of change of momentum is directly proportional to the impressed force. So rate of change of momentum. So that means Pi dot. Okay. So I think all of us are very clear with these things. A very complicated topic, right? So if we consider the rate of change of momentum, okay, let me just take the pen. Okay. Since we have enough time, we can just probably spend some time here also. So then, okay. So rate of change of momentum, that means dp divided by dt. So that is d dt of m into v. So we have got mass constant can be taken out. So d dt of v. So this is an idea which you already have it from class 9 onwards, right? This is mass into acceleration, which is nothing but force, right? So whenever there is a variation in momentum, we know that there is some force acting, okay, and then there is of course an acceleration. This is not the case when we consider velocity to be constant. If the velocity is constant, there is no acceleration. Okay, so all these concepts are still there. Please don't forget this. Okay, these are important here. So what we have here is that the force is is equal to rate of change of momentum, or if we just do a simple maths, we say that Fi minus Pi dot is equal to 0. So this is for the ith particle of the system. So what we do is we consider a single particle, imply an equation on that, and then try to do the summation, extend it for the entire system. Okay, imagining that the entire system will behave in the. For exam purpose, whatever I am explaining, you don't need to write down so many things. For your exam purpose, whatever is there on the screen, you can simply write it down, get your full marks. Okay, but I think I'm just emphasizing on some extra points so that you understand it better. Okay? So we have this, and then we can actually extend it for all the particles. So if we just take summation over I, fi minus pi dot li delta ri is equal to 0, right? So this basically comes from virtual work only. We are not skipping virtual work here. We are just replacing this. We are just replacing it with fi minus pi dot. So just replacing it with fi minus pi dot is equal to 0, and we have got fi minus pi dot delta ri is equal to 0. Okay, so that's important. And then delta Ri is nothing but the virtual displacement. So the virtual displacement concept will remain alive here. It's still there. But then the function that we are talking about here, we have defined it in terms of momentum. So you know, if you can actually define a function in terms of momentum, you are telling more about the motion of the system. Okay, you are talking more about the motion of the system. We'll try to, we will appreciate this fact in the next unit when we are talking more about Lagrangian and Hamiltonian. So if we actually want to again separate out the applied force and the constraint forces, okay, because we can actually have a constant force and an applied force here. So we just separate it out, and then we can get this, and then this is Fi dot delta Ri. Again, we can say that the constant force and the virtual displacement more or less are consistent with each other, and that is why there is no virtual work done. Okay, so we can just say this is 0. So in the last class we did say that if the constraint is consistent with the forces, okay, if the constant forces are consistent, okay, we basically say that there is no virtual work done. Okay, for that please refer to the last class. Okay, I think I have not uploaded the second lecture. I'll upload it today, and then I'll share the link with you. And if you consider this part can again be considered to be 0. No virtual work is done for Fi, and then simply we have this particular equation. So you might say that why we need to do so many things. We can just simply take this, put Fi minus Pi is dot delta Ri is equal to 0. Well, you are right in one way, but the thing is you need to include all the possibilities. So straight away I am not taking Fi A, okay, I am taking Fi plus Fi A plus small fi, that means the total force. And the total force is nothing but a combination of applied force and the forces due to the constraint. Okay, so we will keep this thing here, and then we will put this and write down this equation. So this is the total derivation of D'Alemberts principle. So for your exam, probably this will be around 2 to 3 marks. You can just not skip any line. I prefer that you write down all your sentences and do it. Okay. So in your own leisure time, try to look into this problem and try to understand that how exactly is this solved. Okay, this is actually important. D'Alemberts principle. Now in your syllabus, it also talks about the application of D'Alemberts principle, but let me tell you, there are a number of applications. I'm just going to discuss one, okay, and I'm going to list down 2 or 3. So some of the important applications of D'Alemberts principle is mass falling under gravity. I'm just going to discuss that problem, okay, or this example, mass falling under gravity. Another application of D'Alemberts principle which we are going to look into is mathematically is the derivation of Lagrangian equation of motion. Okay, so for deriving the Lagrangian equation of motion, we are going to use D'Alemberts principle. So that is also an application. But in general, practically, mass falling under gravity can be explained by this. And then this is a very common problem. If any of you have tried for the entrance exams, different entrance exams after your 12th, okay, be it on a frictionless vertical hoop, is basically a very common question that usually comes. You have to write down the equation of motion or remember the equation of motion, those kind of questions. But this problem can also be understood by using the D'Alemberts principle. And then finally, Atwood's machine. Atwood's machine is something which we are going to do in the Lagrangian chapter. We are going to solve it. Okay. So if you consider an Atwood machine, if you consider a machine something like this, you have got a pulley, and then you have got, let's say, a mass m, and then you have got another mass m. This also comes under the laws of motion chapter. Okay, and here if you consider this system, you basically have this acceleration going upwards if this mass is greater. Okay, let's say this is m1, this is m2, and then we say m1 is greater than m2. Okay, so this will go up and this will come down, and then you solve the equation of motion to find out what is the acceleration of the system. So this is actually an example of Atwood machine. Okay, this is an Atwood machine. So we are going to look into different types of Atwood machine, and we are going to take one or two forms of this Atwood machine and going to find out what is the equation of motion for that using Lagrangian. Okay, so we're going to use this classical concept, and we are going to see that whatever you know about Atwood machine is going to be the same thing whatever we are going to derive using classical mechanics, but this will be towards the end of the second unit. Okay, not now. So let's consider this mass falling under gravity. So we have got a mass, let's say m, and which is being attracted, okay, under the gravitational force, and this would be a good example. So we can say that example would be a mass m falling under the effect of a constant gravitational field G. So whenever we have any mass falling, okay, from, let's say, any height, it will be under the effect of G, 9.8 meter per second square, okay, constant gravitational field. Okay, we know that already. And then the force which will act on this mass is minus mg. Okay, we're just using that convention since it's falling, so we'll just put a minus there. Okay, it depends on what convention you follow. Sometimes people also write down plus, but if you write down plus, then you have to mention what convention you are using. So the force on the mass is minus mg, and the work done due to this force under vertical displacement would be nothing but delta z. So there is a vertical displacement which happens, and we will say that this vertical displacement is delta z. So we are just taking this displacement for a very short period of time. Okay, and that is nothing but an infinitesimal displacement. Okay, and that is the vertical displacement we are talking about. So then we can actually find out what is the work done under the gravitational field. Okay, so there are different ways of understanding it. You can consider that the gravitational field is acting as a constraint here, and then we can actually find out what is the work done. So since we are considering a very small displacement delta z, the work done is also infinitesimal in nature, and then work done is minus mg delta z, right? Work done is force into displacement. So our force is this, displacement is this, force into displacement should give you the work done. So this is under gravity and a type of constant motion we say, but then there is also the inertia which is acting on the body, right? So inertia is the property basically of a body which does not allow it to change its state of rest or of motion. Okay, so it basically comes from the concept of using Newton's first law, right? Everybody will continue in its state of rest or of uniform motion in a straight line until it is influenced by an external force, okay, to change that state. So basically there is an inertial force which is also acting here, and then this inertial force would be nothing but mass into acceleration. So you understand this. If you have an heavier body, and if you just forget about viscous drag, resistance from the air, okay, the body actually wants to keep moving, okay, and then that movement is actually affected by the gravitational pull, okay, but then the body also has got an inertial force within it. Okay, so basically when we consider the inertial work done, it will be nothing but minus m d2z dt square into dz. Okay, and then logically we understand that this, whatever value it has, the inertial force must be equal to the acceleration due to gravity. Okay, so if this does not balance the acceleration due to gravity force, that means minus mg, the body will basically have a different effect altogether, right? It's not going to come down. Okay, so that's why this is important. So we can actually take the sum of these two and give set it to be 0. Okay, so we can set this to be 0, and you see that we have used the concept of mass into acceleration here, which we understood from DÁlemberts principle. We use the concept of infinitesimal displacement. We consider it to be a virtual displacement, okay, at least theoretically here. And then we say that this total must be equal to 0. Okay, so when we do this equation and try to solve it, we actually expect this result. Okay, the acceleration due to gravity, okay, must be d to z dt square. Okay, so we can just take the sum and do it. Okay, and I think if we just take it on this side, this will be, yeah, this is correct, right? So if we take here, so you can see this, right? I think this is very simple. Yeah, so we can take this minus mg delta z is equal to m into d2z by dt square into delta z. Okay, so there will be a minus there, so this gets cancelled, delta z gets cancelled, so we have got this g is equal to, or minus g is d2z by dt square. So if you go back to this concept of acceleration due to gravity, we know that this is nothing but the rate of change of displacement. Okay, so this concept more or less remains the same. So it's not that D'Alembert principle, using of D'Alembert principle or using a different approach changes the result. The answer is going to remain the same. It's not going to change. Okay, so if you consider an equilibrium system, the inertial force must be balanced by the gravitational force that is acting, and if you basically equate them, we actually get what is the acceleration due to gravity. So this is the application of D'Alembert's principle. Okay, and I know that this sometimes sounds a bit confusing and sometimes it doesn't sound very convincing, but then it's important that your concepts are clear from class 11, 12, so that you are a bit more into it. Okay, it's very important. So there are two more applications which probably I won't discuss now. Later on, Atwood's machine we are going to discuss later. Okay, so I think I should stop here, because for the next topic what we are going to do is, in tomorrow's class, we are going to use D'Alembert's principle to derive Lagrange's equation of motion. So Lagrange's equation of motion is something which is not should not be very clear to you till now, because we have not put it into application. But after we do tomorrow's class, from the next class onwards, we are going to look into the application of Lagrange's equation of motion, and then it will become a bit more clear. Okay.